Hi, thank you for attending the session. We'd like to welcome everybody, especially you diehards who stayed for the very last session of the day, and we'd also like to thank our live streaming audience for joining us. Today, Fertility Tech is sponsoring this session, EmbryoScope time-lapse system, the new standard of care. I'd like to introduce our moderator for the day is Lily Reed. Lily joined Fertility Tech a little over a year ago. She has a scientific research background in embryo development. She's worked extensively doing trainings and workshops on many of the ART techniques that have been discussed today. She's done workshops on ICSI, on assisted hatching, and many of the other techniques you use. So I would like to go ahead and I will pass it over to Lily.
Thank you. Oh, good. Actually, can you hear me okay? It's good? Pardon me. So thank you, Marianne, for introducing me, and thank you also everyone here. I wanted to, actually, before we start, tell you a little bit about the EmbryoScope time-lapse system, because if I don't tell you what the technology is that we're discussing, you might not understand the high level that you'll hear from our speakers today. And afterwards, I'll introduce you, okay? So here's the EmbryoScope time-lapse system. And I'm not sure if you're familiar with this, but it's essentially two components. It's first the EmbryoScope, which is the incubator, the box you see on the side. And here we go. And there's also a microscope inside and an imaging camera. So if you can imagine, while the embryos are in culture in the laboratory, the embryologist or the lab person can check the embryos during development without having to take it out of the incubator, bring it to a microscope, and disturb the embryos, essentially putting it in a room temperature environment, and then put it back into the stable environment for culture. But not only that can they watch the embryos during the development, they can also have these time-lapse videos later for analysis and documentation. And that's what you see in the bottom. You actually see the embryo viewer. It's a workstation that has the time-lapse videos and also some software for analysis that the embryologist can do on the videos. Okay? And here's our EmbryoScope time-lapse system. It's the latest generation of technology to help you conceive. Okay? And with that, I'd like to introduce our speakers today. Here we are. You didn't expect a picture of you, did you?
No.
With me today is first Dr. Denny Sakis, and he's the CSO from Boston IVF in Waltham, Massachusetts. And Dr. Sakis has had extensive clinical IVF and research experience for reproduction. And he's renowned internationally, having organized many conferences and workshops relating to these relevant topics we're listening to today. And you're a frequent speaker, invited to workshops worldwide. Yes, you must travel a lot.
Yes,
yes.
I'm a frequent flyer also.
And you've published more than 100 peer-reviewed manuscripts and 30 chapters in the field of fertilization, early embryo development, and male infertility. And you are currently on the editorial board of 5 leading journals. Okay, so this is Dr. Sakis. And also with us today, if you would do the,
Oh, there
sorry.
is a picture.
I should tell you, the title of your presentation today, which is Picking the Most Viable Embryo, Past, Present, and Future. Okay? And also, we have Jason Barrett. And Jason Barrett is the lab director of the Art Reproductive Center in Beverly Hills, California. And Dr. Barrett holds a national certification as a high complexity laboratory director with the American Association of Bioanalysts. He's also been awarded the New York State Department of Health certification as a laboratory director in andrology, endocrinology, and human tissue banking. So in other words, he's worked from coast to coast. Yeah? He, besides serving as an embryology director at the Art Reproductive Center, he's also a research scientist and has organized numerous studies contributing to the study of infertility treatments. Okay? And Dr. Barrett's talk today is the EmbryoScope, morphokinetic analysis of developing embryos, or his acronym is MADE. Okay, And with that said, if you'll do the honors.
Thank you.
Oh, one more. Don't forget, this session and all the other sessions are available online. Also, the speaker contact information is available as well if you'd like to speak with them directly or contact them at the fertilityplanet.com website. Okay? Thanks. And with that.
Thank you, Lily. And thank you to Fertility Planit and to Fertility Tech for inviting us to give this talk, and because it's incredibly important. I think one of the main things missing in infertility treatment is patient education. I think if more of our patients knew about infertility and when infertility can strike them, it would be more important. It would actually make our job much easier. So what I'm going to talk about is something that we've been struggling with for a long time, and that's picking the most viable embryo. And I'm going to talk about the past, the present, and hopefully how the future will be for patients and for the laboratories such as ourselves. So there are problems with assisted reproduction. The biggest problem is the majority of our patients, unfortunately, fail to get pregnant every time we treat them. The other major criticism, which is actually, it's less proportionate to the failure of pregnancy, but there's a major criticism in IVF in that a lot of pregnancies lead to a multiple pregnancy, and that actually causes us a lot of the bad press that we get. But to allay this criticism, the IVF community is being compelled via either illegal, so in some countries, especially Scandinavian countries, it's illegal to transfer more than one embryo, by financial, which is probably what will happen in the US, where the insurance companies will eventually wake up and work out that it's actually costing them more to support multiple pregnancies than it would to actually to subsidise IVF cycles, or actually even a moral obligation. So as a lot of societies, even our own society, the American Society of Reproductive Medicine, has actually brought out guidelines telling us when it's better to actually transfer one embryo or even transfer 2 embryos in patients. So these changes in the way we practice will compel us or restrict us to transfer only 1 embryo and restrict the number of embryos transferred. So how do we get to single embryo transfer? Well, we need to establish a more rigorous selection process for defining the quality of individual embryos. And we've actually heard a lot about that today. And the whole aim with all these technologies that we're listening to is to help us in the laboratory and help the clinicians and the patients decide which one embryo may be the most viable and lead to a pregnancy. And the limiting factor all along, for the last 30 years that we've been doing this, is that the measurements ideally need to be non-invasive or not hurt the embryo. PGS, for example, is an invasive technique, but it doesn't harm the embryo. But the other problem is we don't really want it to be time consuming because we do have time limitations, although some of these are being allayed now. So there are some constraints to the types of technologies that we can offer. And obviously another constraint is how much these technologies will cost eventually to the patient and the clinic in time and money. So we've really relied since the first pregnancy on a morphological assessment. And it's not that current. So we talk about morphological assessment, but it's not a new idea. And the things that we're trying to do today and the things we're discussing about cleavage rates and taking videos of embryos is not that current an idea. Even the godfather of IVF, if you want to call, Sir Bob Edwards, who was the Nobel laureate for reproduction, stated in one of his initial papers that cleavage rates on a certain day and overall embryo morphology were valuable in choosing which embryos to transfer. So this is the first pregnancies. People realised that looking at the timing of growth of embryos and looking at the morphology were very important characteristics of an embryo. And even other people, other studies, even in the early 80s, started looking at giving a score to embryos to see which embryo was the best embryo. So this concept of looking at time, when an embryo was developing, and its actual morphologies is actually a concept that was there right from the start of IVF. So the other concept is that we've known, even the way we've sort of crudely been doing morphology, that we knew when we had a nice looking embryo that the chances of that embryo developing to a pregnancy were much better than the ones that didn't look that good. If you look at this graph here, for example, this is from single embryo transfers. So this was a study that we were part of in Amsterdam, so in Holland, where single embryo transfer is mandatory by law. You cannot do transfers in duplicates or multiple embryo transfers. So here you could really look at the quality of an embryo for morphologically and see what its chance of giving a pregnancy was. On the left, you see excellent embryos. So this is excellent looking embryos on morphology. And you can see the red bar is quite high here. So the pregnancy rate is much higher. But if a patient only has sort of poorer looking morphological embryos, it doesn't mean they won't get pregnant, but their chances of getting pregnant is much lower. So this is an indication when you put one embryo back and how it looks like morphologically on day 3, what the chances of pregnancy are. The better looking or the excellent looking embryos have a better chance than the ones that don't look as good in morphology to the embryologist. So the one on the left is the good one, has a higher chance, and the one on the right is a poorer looking embryo, but still has a chance. So the trick is in us identifying what are the characteristics of these types of embryos that lead to a pregnancy, even though now we have this crude way of looking at embryos. So the past and present morphological assessments, we know that we've been after 2 different sort of parameters that we've been seeking to look at. The assessment of morphological markers at different stages. So we've grown very good at looking at different traits of embryos and how they look. But we've also, one of the things that we've really lacked is looking at these parameters at particular time points. So we've always had a problem trying to maximize the time points that we've been looking at embryos. So this is just an indication of how we currently look at embryos and how now we're starting to use video time-lapse to look at embryos. So when we say we've looked at embryos on day 1 or day 2, or someone gives you a call and tells you we've looked at an embryo on day 3, we look at them mostly in the morning, but the time is actually not very precise. So when we look at embryos, we look at them at day 1, so they should be in the late afternoon. A day 1 embryo will be about a 2-cell stage. On day 2, we look at them at about the 4-cell stage, and on day 3, they'll be between the 6 to 8-cell stage. But really, we only get a static look at the embryo. We just look at them once and we put them back in the incubator. So we're not getting that much information. And if you look at here, the graph here shows how, if you look at the green line, this is an embryo that cleaves faster or grows faster than an embryo compared to the red line. But there are certain times, about 10 or 12 hours, where an embryo stays at the 2-cell stage or the 4-cell stage or the 8-cell stage. If we're looking at an embryo, say in the middle of the day, and we see that it's a 4-cell stage on day 2, for example, we don't know if that embryo has gone to the 4-cell stage an hour before another embryo that we may look at. So we lose a lot of information. So if you're looking at embryos statically, you're getting just a snapshot of what's happened. But if you are able to look at embryos continually and get a lot of pictures of them, you actually get the information where the green and red lines distinguish between an embryo that when it went to 2-cell, when it went to 4-cell, or when it went to 6 to 8-cell. So we get much more information if we do a continual assessment. And that makes normal sense to anyone, I hope. And we've known, even looking statically at embryos, that the information on looking at cell stage and looking at timing gives us a lot more information and the ability to predict a pregnancy result. This is a study out of Sweden where this was an old study, so not using these embryo technology, video technologies, but if you're able to look at a single embryo transfer where you've looked at an early 2-cell cleaving embryo, so you're able to identify the embryo that went to the 2-cell stage first and you transfer it, you can get a double pregnancy rate compared to embryos that did not go to this early 2-cell stage. So just looking at timing and cell stage already statically gives you a bonus in choosing which embryo will lead to a pregnancy. And we also know from a lot of data that when you can pick a very nice blastocyst on day 5, that the chance of that embryo becoming leading to a pregnancy is also much greater. So patients that have nice blastocysts with different components. And here you can see there's a little ball of cells on the right, which is called the inner cell mass, and that actually leads to make the actual fetus or the baby. The cells around the thin layer of cells are called the trophectoderm, and that leads to the placenta. So what we do when we're looking at blastocysts is we score all these. So we look at all these and how they've developed, and we give them grades. So we know that a nice blastocyst has a better chance of giving you a pregnancy. So, and we know this because in pregnancy outcomes, when we have very nice looking blastocysts, such as the ones on the left-hand side, our pregnancy rates can be very elevated compared to one where the low score or poorer looking blastocysts are on the right-hand side. But remember, this is just looking statically at embryos, and also just because you don't have a beautiful blastocyst on day 5 doesn't mean you'll never get pregnant. So the information, we're missing a lot of information when we're just statically looking at embryos at one time a day. Because what happens is we have this picture in our head that there's looking statically that we should hit certain landmarks. So on day 1, an embryo in the afternoon should be a 2-cell. On day 2, it should be around the 4-cell. On day 3, it should be an 8-cell. And these will give us a much higher chance of getting a blastocyst, doing a transfer, and getting pregnancy. So the likelihood of forming a blastocyst and getting a pregnancy is much greater, we believe, when an embryo actually follows the correct path and follows all the right patterns. But just as when you came in today to New York, I'm sure a lot of you took different roads. I don't think everyone came in the same path. So embryos can get to the blastocyst by various different stages. So they can look good at one day, they can look poor on another day. So the paths that an embryo can take to get to the blastocyst are really different. But the end, sometimes the end when they get to a blastocyst or they lead to a pregnancy, not all embryos took the same path. So we're unable to get that much information when we're looking at embryos just statically one time a day. But what we're learning now with video technologies is that we can actually get much more information. And we're learning a lot in the laboratories when people in laboratories are using these different technologies to see how embryos actually get to the blastocyst stage and which embryos lead to the pregnancy. So we're learning a lot about these different paths embryos can take. So the biggest question for us is when we have an embryo from patients that look very similar, which one do we transfer if we want to do a single embryo transfer? And as I said, the embryos can take different paths. And when we look at them just one time a day, we lose a lot of information, and it's much harder to make that decision of which embryo to transfer and which embryos to freeze. So the video technology, we've always thought if we had a nice video technology, we would be able to make these decisions much easier. And this is not a new idea. So since the early 80s or the late 80s, people have been playing around with systems where they've put cameras on microscopes and tried to video embryos. There's been so many studies. Jacques Cohen, who was a speaker earlier on in this session, or today in the Fertility Planit meeting, had actually developed technologies looking at using videos to take videos of embryos. And there have been a lot of papers where people have tried to video embryos to get a lot of information to see which embryo is the one that will give you a pregnancy. So it's not a new idea. But now we have systems, and the sponsor of this session, Fertility Tech, has provided us with a nice incubator. And we saw in the previous session, there are other companies that are looking at this technology. But this is a system where you actually have an incubator also, plus the video technology. So on the left-hand side, this is the incubator that actually contains the embryos. And the embryos stay in this incubator for 2, 3, 5 days, depending on when the patient will have a transfer. On the right-hand side, you have this viewer that actually allows you to look at the embryos continually. So I can go home, I can come in the next day, and I can see what happened during the night. I can go back to my office and sort of come in and look what happened. I can come in and make a decision about an embryo because I have all the information about how it's grown from day 1 to day 2 to day 3. So I haven't got these static time points, but I've got a continual line of development that I can look at all the intricacies of the development. And the way this works is that the embryos are placed individually in little wells, little very small wells that are moved in the incubator, and a little microscope, video microscope, takes continuous movies of these embryos. So on the left-hand side, you can see like a little well system where embryos are placed individually. So they're one by one, so we can track and we know exactly which one belongs to which embryo, which video belongs to which embryo. And these systems take multiple slides, so we can run numerous patients in these systems, and it's a very safe and secure system. So I'll just show you the type of information we get from one patient, for example. So the beauty is we can compare different embryos and we can run them alongside each other. And here you have 3 embryos, and this patient had 10 embryos, for example. But if you play the video, you can see there are 3 embryos here, and we can compare their growth one side by side and just see how each one grew. And you can see some do things differently from others. So the one on the left-hand side just went to the 2-cell stage now, but there's 2 others that seem like they're growing much faster. So we can look at these and look at them continually to see what's happening with these embryos and make decisions about what they did during different stages. And you'll see here 3 embryos that look very similar. Maybe right now if I looked at them and I was doing a static assessment, I'd come to a different conclusion than I would if I actually had all the video information. So if I looked at them now, I might pick embryo number 3, the one on the far right, as the one I would put back to the patient. But if I looked at the whole video, I would see that each of these embryos had a different way of getting to where it was at that particular time. And you'll see that some of these embryos actually have a different history, or they finally have a different fate. So you will see that they start growing very similarly, but then as we go along, they actually change in the way they're developing. So the one on the far right, you will see, actually starts growing much more poorly, so it's not growing that well. Whereas the one on the left and the one in the center are showing better features of development. So what happens with these is the one in the center actually on day 5 becomes a really nice blastocyst, and you'll see it disappear in a minute because we transferred it back to a patient and she got pregnant, luckily. And the one on the left actually becomes a nice blastocyst a bit later than the one in the center, and we actually froze it later on. Whereas the one on the right, even though it looked very similar to the other 2 embryos initially, actually we couldn't freeze because it wasn't very good quality. So we get a lot more information from having these videos and being able to compare embryos, whether it's 2, 3, 10, 12 embryos, and we can compare these embryos and see how they've developed using these time-lapse systems. So it gives us much more power and much more information about how we select embryos and how we choose which ones to transfer, which ones we freeze. So static morphology, which we've been doing for the last 30 years, has probably taken us as far as it can, I think. It's helpful, but it's not enough for us to actually go and do the single embryo transfer to have as much information. At best, the morphology that we've been using only serves to give us a subjective idea of which embryo was the best embryo. And today, these video systems, these morphological assessments using real-time videos of the embryos, similar to what we see with the EmbryoScope, allows us a rapid and easy, non-invasive analysis of embryo selection. So we can leave the embryos in there for 3-5 days and we don't touch them, but we have all the information we need to do a morphological selection. So morphometric real-time analysis will play a really big role, I think, in the future of routine embryo culture, because it will provide us a greater capability to distinguish between individual embryos. It allows us a more stable environment because we don't need to take the embryos out to look at them. And it gives us much more diagnostic information for the embryologist, for the clinician, and the patient to make the decision of which embryo to transfer. So we've seen today a lot of different technologies, so patients are probably being overwhelmed with technologies. But what will happen in the future? I think we're going to move more to blastocyst culture if we're looking at doing single embryo transfer. Real-time morphology will give us much more information diagnostically of embryos. But within these, you're going to have other techniques that you're going to look. We're going to be able to examine the metabolism of embryos, the types of proteins they've secreted. So all these technologies will be available and help us make a better decision of which embryo to transfer. And of course, as you saw in the earlier sessions today, we have a lot of genetic information of embryos. So all these technologies will help us make the decision and more personally diagnose which single embryo to transfer and which ones to freeze, and hopefully improve the chances of all our patients to get pregnant. Thank you.
Thanks, Danny. Wow, that didn't come out looking exactly like I wanted it to.
Oh.
The MAID down at the bottom doesn't work very well in this screen adaptation. So I'm Dr. Jason Barrett. So I work as a laboratory director in Beverly Hills, California, where we happen to have one of the Fertility EmbryoScopes. And I thank you guys for allowing me to come talk about the good work that we're able to do with the technology you guys have provided, as we're excited about it, and I think ultimately it's going to be really good for patients. So with that being said, I'm going to try to discuss it a little more with a few more videos, just because I love them, and talk about how we use what we are now calling a morphokinetic analysis of the developing embryos, or finding MAID embryos, using a little bit of my New York family type acronym. So that's what I'm going to talk about. So in all, as you heard from Dr. Sakis, the EmbryoScope is an integrated time-lapse microscopy with microincubation. So everything built into one box. So basically, you don't have to open it. And because you don't have to open it, you don't change the culture condition. It is the most optimal it can be the entire time it's in there, giving it the best chance to survive. Anytime you go outside of the normal, optimal environment, you are compromising the future development of that embryo. So in this case, you don't have to take it out. But you get more than 100 observations every single day of every single embryo. And you get 7 focal planes inside an embryo, so you can go in like 3 dimensions up and down through it. So you get over 3,850 images over a 5-day period. So that is a lot of pictures to look at. So it takes us way more time to look at all these, but it gives us so much more information about them. So additionally, it allows you to very tightly control those temperatures, the gas source, and the dishes that you use, the media and the oil. You can easily see differences if anything goes wrong very, very quickly, because you're getting constant information. It's not, oh, you have to go a couple weeks after and find out this, that, and the other. It is immediate and instant. You can look at that thing and you can go backwards and forwards over many, many patients very quickly and diagnose anything that might not be right across all patients or within individual single patients. And that tells you the difference between them and somebody else and what may or may not work for them. So, so we have one of these units in our place, and we use it for the morphokinetic analysis of developing embryos, or MAID, through the video analysis. And so we sit at the scope, myself and Dr. Hill, who's the other one that sits there, and we look at them. We look at all 12. So here's the display of a situation where there's 12 embryos sitting in the EmbryoScope, each one of them their own little well. And we play these videos over and over and over, go backwards and forwards many times, and look at the micro differences between one embryo and the next in order to rank them and ultimately give you the best choice of, we hope, one embryo at a time, in order to give the highest percentage chance of success with also the lowest percentage chance of having an abnormal pregnancy develop, because that only slows down a person's development, slows down a person's progress through treatments of fertility, and leads to very difficult choices being made. So this we're going to call the nice blastocyst. So I'm going to ask Kevin to go ahead and play it, and you'll see, whoop, no, I got to go back one. There you go, and play. Here we go. All right, so 1 cell, 2 pronuclei develop. I don't have the pointer there. 2 cells develop. Denny's pictures was a lot slower. I sped it up. That's 4 cells. There's 8 cells. Everybody's progressing along. That's 3 days of growth that you just saw in like 10 seconds. Develops into a morula, develops into a blastocyst, and expands and expands and expands, and then it starts to hatch out. That's what we want to see. Now that was sped up really fast compared to what you were showing them. And there are reasons that we put it together real fast like that. And any patient that actually gets pregnant, we actually give them baby's first video of that exact type of thing, because you can't get a video earlier than this. I mean, there's a sperm and there's an egg, and well, you can't do anything there. And after that, you can get this. So we give this away as a nice little treat when they can get pregnant, so that they have a very early baby video. But so that's what a nice one looks like. That's what we want to see. Ultimately, there is an inner cell mass in there. If you focus up and down through all the 7 planes, you can see it very well. You can make nice, beautiful discussions about why you picked that one over another one. This is an embryo doing something wrong. It's going from 1 cell to 3 cells. There is no correct biological way to divide the chromosomes correctly at all from 1 to 3. It has to be dividing from 1 to 2. It can't go 1 to 4. We can't go any other things. 1 to 2 is the only way it can go. So in this embryo we're going to watch, go ahead, Kevin, thank you. You go from 1 cell, 2 pronuclei develop. We knew it was normal. And then all of a sudden, it gets crazy. It doesn't know what to do. It's wobbling around. Who's who? What do we want to touch? Who's going to be together? And we end up with 3 cells at that stage. But we watch it, and we go ahead and let it continue in there. And we saw something bad, but we're going to continue, and we continue, and we continue. And we actually see that it still does form, when you go all the way out, a blastocyst. Now, if you only look at very specific certain time points, like Denny talked about, those static observations, you would see a blastocyst at the end that's hatching out and that actually does have an inner cell mass. Not the most beautiful one, but it's got one. And it would be in your possible transfer pool. But we know very early on, in that first division, it already did something so wrong that it has about only a 1% chance of working. If we looked at static observations, we would never see that. You would never know how it got to being 3 cells. You have to see that in the middle of the night when none of us are at work, but the machine is continuously working for us. So that's an abnormal division, which allows us to eliminate that embryo from the possibility of transfer, because it will only lead most likely to either very, very poor success rates or to an abnormal pregnancy, which is a worse thing for the patients. This next one does 2 cells into 5. Once again, a completely abnormal division. There's no way to divide. So when I, go ahead, Kevin. So you'll see that it forms 2 pronuclei, perfectly normal, perfectly healthy, looking good. It divides into 2 cells, and then you'll see, boom, there's all of a sudden 5. Wait a second, that means 1 went from 1 to 3. But if you speed it up and watch the rest of the 5 days of development, you can actually see it does begin to form a blastocyst. Definitely telling you that if you had looked at the day 3, it had many cells and there's a possibility of transferring it. And if you looked at the blastocyst, it has a blastocyst formed, not the best one, but it still has formed the blastocyst. So you would still potentially pick this embryo for transfer, or possibly choose it to be frozen for later use. But the success rate is still in the 1, maybe 2% chance of success from an embryo that does something like this. Genetically, you cannot divide the chromosomes correctly when you do anything other than an exact equal half distribution. All right, so this one, in a second, what we're going to do is you're going to show you how an embryo shows you multinucleation, shows you an abnormal nuclei within an individual cell. There's going to be more than 1 cell at this point, at the 2-cell stage when he plays it in a moment. You'll actually see there's multiple clearish areas. That's telling us that it has not put the chromosomes together in the correct way. It has not aligned everything correctly. It is not prepared in order to duplicate and segregate the chromosomes normally. Most often, this leads to a significant decrease in the percent of implantation for an embryo. It usually cuts it by more than a half, if not completely eliminates it. So go ahead, Kevin. And so you'll see it divides into, so there's 2 normal pronuclei, divides into 2 cells, and in some of those cells you see 3 and 4 different little nuclei. Once again, it divides to 4 cells, it keeps going along, and as it goes along, we'll speed it up here in a second, it continues to develop. The key is that that would never be seen unless you have this technology working 24 hours a day. It does not get noticed. There is no way you would have seen those. It happened at something like 3 in the morning if you look at the timings on that. And if you miss it, you will never see it potentially again. But that did form a blastocyst. Yes, once again, not the most perfect one, but we're always ranking them in the best situations, and this tells us something that would eliminate that one from being transferred, or at least wouldn't put it in the top tier of embryos to be transferred. So something else we look at that we would never see any other way. So which embryo is the best? So going to play this one. There's 4 embryos. You look at them all, of which ones you want. So I've told you a couple little things. So go ahead, Kevin, play it. Try to pick which one we think would be the best, which one would be the transferred one. And if you look at them there, they all had 2 pronuclei. The ones on the upper left and the lower right divided to 2 cells faster than the other ones. We've gone along there. You actually see some multinucleation in the bottom right one when those 2 cells. The one on the upper left is fastest. It's 4 cells already. The other ones were a little bit behind that. So it goes along. And then I'm going to speed up the video because I don't want to take forever with it. And you see them developing along some form of morula before the others. They keep all expanding. So everybody formed a blastocyst. So which ones do you put back? Well, I'm going to tell you that upper left one, it divided faster than the other ones. So you'd say, ooh, that's the best one. Well, ultimately, it didn't form the best blastocyst out of the whole thing. The one on the lower right had multiple cells with multinucleation, probably wouldn't have led to a normal development. And the one on the lower left actually divided from 2 cells to 5 cells and showed us a very bad thing. So only the upper right-hand one is the one that has the highest chance of success. But you need to know how it got from 1 cell all the way to the blastocyst in order to make the best decision possible, to rank them out. I'm not saying the other ones can't make babies, but they don't make them nearly as often. And if we use the technology of looking like 3,000 different images across every embryo, we can find these minute, small changes that really decrease the chances of having a pregnancy. So we use also time points in development. So in the oxygen discussion, previous group, and in this group, you actually find that there are time points of when embryos need to sit and rest, when they need to replicate by, if they take too long or they take too short a period of time, and watching for those bad signs that I just showed you about. So we can use those time points, time to get to 2 cells, to 3 cells, time it rests between 3 and 4 or does not rest between 3 and 4. Does it go too quickly between things? We use all of these things and start to rank which ones are the most important when we get past eliminating the abnormal divisions. So that's what we start to do. We sit there with the embryos in the EmbryoScope. We look at them all individually, and we make, on the right-hand side, you sort of see this orange, green, yellow, orange bar that goes up and down. That helps us track when major changes have happened. As each one of those bumps goes up, it's telling us that it divided or did something during that period of time. And we concentrate on those changes and divisions, and we track them, and we can rank each thing that happens, each 2 cell, 3 cell, 4 cell. And by doing that, you get all the time points of how long it stayed at each one. And those become important when determining what are the best embryos. So here actually is the EmbryoScope on the left-hand side, and Dr. Hill, who's my direct boss, and I'm on the right-hand side, and we're going through a set of, in that case, 7 embryos on that screen, looking at them all through their entire developmental history and trying to pick what are the top 1, then number 2, then number 3 to make the best decision for the physicians. And then we track it. We actually print up a picture from it, and we send it off to the physician and the patient so that they can have the appropriate discussion about what has happened. We tell them all about different reasons that we suggest one versus another. And then ultimately, if they become pregnant, we take those and we go ahead and give them a video. So we do a lot of review of every embryo's development. So you can go ahead and start this one, Kevin. So this happens to be a set of 11 embryos that are in there. And we look at them all, and as they develop, there's the 2 moving along. Some of them are about to go to, come on, 4 cells. You want these things to keep going all the time. You're like, come on, I know you can do it. But we go backwards and forwards many, many times to look at them. But we look at these things, and they advance along, and we track every single one every single day, and we look at every picture to see if we can ever catch a problem. But we look at this whole set of 11, and we knew which ones were the better developing ones and which ones weren't by analyzing how each one developed across each time point. We then can use some of the literature has found, and some people who have a lot of time-lapse experience have found out that there's a number of ways to segregate which embryos are the best and such. So they start with how do they look morphologically, and all the information that we've known about that. And let's say morphology is like 35 to 45% accurate, and it's worked for a lot of IVF for a lot of years. But this goes beyond that. It takes you to a complete other level. If you look at the things that did the 1 to 3 or the 2 to 5 divisions, or the things that have the multinucleation, if you take those away, you've eliminated a lot of embryos that have almost no chance of working. You know, the 1 to 2%, maybe up to 15% maximum chance of working. If you take those out of your pool, what's left has a much higher percentage chance of success. And then in this case, we can use times that the embryo reached certain stages, either the 2 cell or the 5 cell stage. And if they reached it within the window that is most optimal and that is shown us by known babies produced, if it reaches it in that window, we know it's a better embryo than another, and we can rank it a much higher embryo. And so at the bottom, you actually see there's some A+ type rankings all the way down to, well, in the end, discarded on the far right. But we can actually go through and rank them in those categories and be very, very specific to the physicians and the patient of which is the number 1, number 2, number 3 embryo, and what that grade would be. And those things absolutely correlated with the implantation potential in babies being produced in randomized trials and in non-randomized trials all over Europe where they were doing this initially. And in fact, there was more recent paper out of the English group that definitely showed that they had success with this increasing pregnancy rates more than 20% because of using this technology. So we can use the analysis and we can rank all of them and get which ones are the green ones, which are the most optimal, versus the ones that are the blue, the second or third level that we'll probably freeze and save for later. And we can give all this information to the patient. So in conclusion, this is a completely non-invasive technology that allows you to absolutely look at the embryo continuously, maintaining very, very high quality control of your culture condition. So you increase the chances of success because you have not compromised the embryo development at all. It's continuously observing everything, and you can see and relate all the developmental differences one embryo to the next, which absolutely show you the differences in success between one pregnancy and another, and which does work and does not work. And the made embryo, the morphokinetically analyzed development embryo, is very crucial now in selecting the single most optimal, because we don't want to create multiples. It's not a benefit to the patient, even though many people ask for it. It's not a benefit to the patient or to the children. One at a time is the way to go. The body's designed for it, and we'd like one healthy, normal delivery every single time. So with that, I want to say where we're going with the technology is moving along and advancing quite rapidly. We can now ask for a second opinion of somebody else remotely. And on my cell phone, I have patients in it right now. I can go in and look. I'm here in New York. They're growing them in LA. I can go in and give a good analysis. So the technology is allowing us to not only have more information to analyze and to make a decision, but we can do it and do it anywhere that needs to be done at any time, and have second opinions by people who have experience and knowledge to be able to make the best decision. So with that being said, I happen to work at Art Reproductive Center on the left-hand side. My boss is David Hill, and I work for the lab that is at Southern California Reproductive Center and the 5 physicians that we work with and who use this technology in our place. So thank you.
Great. Thank you so much. Thank you. So I guess it's time to ask questions. Yes? Yes.
Yes?
How much of your pregnancy rate changed since you implemented?
Because of the limited number of patients that can go into an EmbryoScope at a time, in this case, each EmbryoScope can hold 6 slides. We often find that a patient has more than 12 embryos. That's the max per slide. We often have to use more than 1 slide for positions in there. And how we have selected the patients to go in there. The technology would be great for everybody. Absolutely wonderful for everybody. But we can't put everybody in it. We treat about 60 patients a month. And they live inside here for 6 days. I can't put too many in here, so we have to be really selective. So we've chosen at this point to start with some of the most difficult possible cases, the ones that we think something must have gone wrong during development, but we couldn't see it using static observations. So we've put them in here. In those cases, we've explained to the patient 50% of the time why they don't have any good-looking embryos and why they probably are not getting pregnant, which has led to them choosing to use either other technologies or adopt and that type of thing, because we've been able to show them how it is not working in a normal way. So you take that patient population out, they haven't succeeded because we did the technology, but they have moved along and are no longer trying futile attempts because we can now prove to them why it didn't work. We've also used it for the patients who are going to absolutely positively do a single embryo transfer. And in those ones, they already were doing pretty well, and we've seen about an 18% increase in those ones. The other patient population who is using it, and we are trying to use it in a positive way, and we're all starting to get there, is to correlate time-lapse videography with genetic or non-genetically normal embryos. And so we are doing a number of PGD or PGS type patients in there. So we're getting both their morphological analysis, and we're getting their ultimate PGD, normal chromosomal complements. And we're starting to get to see where there may be some abnormal divisions or that type of thing that are leading to abnormal chromosomes, so that we can start to get a non-invasive genetic test or genetic prediction, not test. And so we're using it for those too. That doesn't increase the pregnancy rate. That only increases the number of embryos that we have to be biopsied, because we're actually seeing over a 15% increase in our blastocyst rate in here versus our normal incubators. So we actually have more embryos to have to biopsy and more embryos to have to freeze for future babies because of the technology. So it's not just we increased the pregnancy rate, it's also many other things that come with it, including the patient education side of it. And let me tell you, when you hand them a my baby's first 5 days video, then they've succeeded. There's a lot of positive comments for the entire office, which is good for morale and helps all of us be even better for the next patient.
That is powerful. Powerful.
It is a very powerful technology. You guys have something very good, and we are trying to use it in every possible way.
And that's an immediate return. You were saying that the doctor-patient communication, that's so crucial, I think. I mean, just going to the doctor, sometimes do you feel when you go, you feel like you don't know what questions to ask and you wish you had some type of visual, something to start. I think this is excellent. It helps educate, and I think a lot of people now are a lot more educated with just, this is the digital age, you know, even with the time lapse, we're moving from analog to digital. So this is very important that everyone's educated in this. Yeah, good.
Very informative presentations. I have a general question if either of you would like to respond. Do you have any thoughts on computer analysis of the cell division and the blastocysts? There was a slide earlier today that talked a little bit about it, but you're the experts. Maybe you could tell us where that's going?
So, you know, we have a lot of data. As Jason mentioned, you know, we've gone from 5 sort of morphological data points to 3,850. So of course for us it's becoming more difficult to sit there and analyze how things, you know, are developing on each individual embryo. You know, if we've got 60 embryos going through the lab in one day, it becomes difficult. So of course we're going to refer to algorithms. And the way, you know, I think the groups are looking at it, and it goes to the question we asked before, that was asked before, is how much has your pregnancy rate increased? These are new technologies, so there's an element of we have to teach ourselves how to use the technologies also. Part of that means that Jason's lab may see something slightly different to what I would see in my lab, maybe a half-hour difference, maybe a 1-hour difference. You know, we don't do everything exactly the same. So we also have to teach ourselves, and within part of that teaching ourselves is actually to develop algorithms and actually work with the companies that provide these technologies to create those algorithms to see what works best for our system. And it may get to the level where we don't have an algorithm for the clinic, but we then start looking at algorithms or models for particular patient groups. So what may suit a patient who is under 35 that has 20 eggs available may be very different from the patient that is over 40 that has only 3 or 4 eggs available. So we may actually be looking for different things. So it's going to be very complicated, but the more data we get and the more data we're able to feed back to the companies, to talk with each other about, you know, what works for me, what works for another clinic, we'll have very powerful tools. We saw with the genetics discussions today that all the information you get from microarrays, all the gene testing, all the different SNPs you can look at are able to be used because we can apply computers to do bioinformatics and give us an analysis of that information. It's exactly the same for us with the video technology. All that information will, in the future, be used through algorithms, and through algorithms that are probably honed in to different patient populations, and that's the power of these technologies.
I'll add one more point to that. I probably don't use the same media that he uses, probably not the same oil. It's not at the same time. We're probably different sea level. And all those things matter. Our gas suppliers are probably different for providing our CO2 and our oxygen sources. So those things probably will affect the embryo development just slightly. And that's why a comparison of his exact timelines and his development, and if this system had a pre-programmed system that it's either in or out, it might not be exactly the same for his lab as mine. We would want to shift that just slightly depending on growth and advancement of the embryos. So with that being said, there are going to be some differences center to center for what they use and how they use it. Additionally, patient to patient, as you're saying, it may be very different for patients who are above 38 in what we should expect versus patients who are not in that bracket. What we see from donor eggs in the use of everybody's lab without time lapse is, wow, they move along very nicely, they get lots of good embryos. In fact, we split donors maybe many times in cases to give multiple babies from the same cycle. those will probably move faster in its development, and actually you'll probably meet those perfect time points even better in that patient population than versus another. So we will have to adapt and constantly do it. The advantage of potentially another system was it does the analysis for you and sees when things divide by itself. That technology exists, absolutely. It's being validated at this point. It's working well in those hands. But that's only for the first few divisions, which I did talk about a few of them being bad. So they are very important ones. And both systems are showing that the same things and the same time points are actually very valuable, whether the computer sees it or a human sees it. A human has a little bit of an advantage as it goes farther along, as you get to more cells and such. The membranes are closer together and may not be able to be separated, and then there's no way of doing anything for the morula or the blastocyst at this point. There's just too many cells and too many membranes. So there is some advantages and there are some disadvantages with computer use only. But we're all getting to the same answers of what is the important time points, what should we eliminate, what should we not transfer, and then how to rank the ones that are still available, how we rank them in those spots based on how they reach certain time points at certain times and what range of acceptability we have. As we get better and better, our ranges get tighter and tighter on what we think is the most optimal, but not everybody lands in there, and so you have to still pay attention to what is outside that because they still have a chance, just may not be as high.
Any more questions? I'm not quite sure on time, but I think we're
We
about,
still have a few minutes left.
we have a few more minutes.
So as an addition to what you're asking, we really are getting to an age of personalised medicine. And the more these technologies, the more data and more information we get, it's easier for us in the laboratory to personalise treatment for particular couples. So that's where the more information we have, the better we are to treat couples and to either treat them to get pregnant or to give them a better diagnosis to move on with different treatments, and which is all important because I think what we're after is getting the patients pregnant, but actually it's also important the time to pregnancy. I think, you know, all our couples, whether they're from California or from, you know, New England, they're all impatient to get pregnant. So the earlier we can give them a diagnosis or a pregnancy, the better it is for the couple and for us as a clinic.
And I'll somewhat piggyback on that. It actually takes more work to do this, but it's better as an outcome. And so we in the lab actually invest, I think I calculated it out, the amount of time I spent analyzing a single picture on one day versus the way more pictures in one day, because I was looking at 400, you know, with multiple lines of everything in one day versus the one picture. I calculated out that I spend about 10 minutes per embryo if I really want to sit there and track everything right, versus about 13 to 15 seconds per embryo when I analyze one single image. So it takes a lot more work for the lab, but we feel that it's worth the time to really help the patients get the right embryo and the best one single back at a time, by far is helpful. And then in the cases, as I discussed, that don't end up in transfers, we can go through it with the patient tick by tick by tick, every single one, and show you where it didn't go right. And that is visually and discussion side by side with the physician and or the laboratory person to really help you understand what has not gone right and the options that you have after that. And that is a extremely valuable thing for the patients. We are visual. A lot of us are tremendously visual. This has so much visual potential with it. And sitting in a doctor's office, making the decision on the transfer, you can sit on that computer screen and you can go backwards and forwards, and know why we did something. As I said, it takes us a lot longer to tell you why, but it provides the information, and that's what the patient's actually after, whether they're going to have a transfer or not.
More educated conclusions, definitely.
Yep.
Yes. Good. Well, I think that's it, unless we have any more questions from the audience. No?
No, thank you all for sticking around to the end.
Definitely. And before we all go, I wanted to thank everyone. I also wanted to remind everyone, too, that on the Fertility Planit website, you can catch this session plus all the other ones by video, and also get the contact information of our guest speakers if you'd like to have more questions and have them answer you directly. Also, I'd like to thank the Fora.tv group, who did all of the AV and did all these nice videos and helped us get all ready for this. And also, of course, definitely thank you to Dr. Sakis and Dr. Barrett, because I could not have answered any of those questions, and now I feel much more educated myself. Thank you. And thank you to all of you. With that, goodbye.